Section 24.2. Now we're going to talk about the magnetic field, or the field that is established by the presence of north and south poles on, for example, a bar magnet. The field, again, shares many similarities to the electric field. It has direction and magnitude. It is therefore a vector field. And the way we can tell its presence is by its effect on magnetic dipoles. As we were able to determine the effects of the electric field by placing a test charge in its vicinity and watching the behavior of that test charge, for example, measuring forces on that charge and in which direction those forces were experienced, we can assess the nature of the electric field in which that charge is immersed. Likewise here, the basic unit of magnetism is the bar magnet, or the bar magnet, or the magnetic dipole, not the north and the south poles individually, but the north-south combination in what we call a magnetic dipole. That's the basic charge of the magnetic field, and if we place that dipole in the vicinity of a magnetic field, it will line itself up. The north pole will point in the direction of the field, and the south pole will point in the direction opposite to the field. Every magnet sets up a magnetic field in the vicinity around it. And the bar magnet here experiences a torque as a result of being placed in the magnetic field, and you can see how that torque serves to align the dipole so that it's parallel to the magnetic field. The force on that dipole, which in this case is really a torque, is able to measure the strength of that magnetic field. The stronger the torque on that dipole, the stronger the magnetic field be. This is very similar to what we saw for electric fields, where the force on a test charge is related to the strength of the electric field. The stronger the force, the stronger the electric field. And you'll remember that the electric field was defined as the force per unit charge, or the force on a test charge divided by its value of charge. That's what gave us the magnitude. In this particular case, the size of the torque, the magnitude of that torque, tells us something about the magnitude of the magnetic field, and the direction is evidenced by the alignment of that magnetic dipole with the field. A magnetic field is a vector because it has direction and magnitude, and the magnitude or the strength of the field is denoted by the letter B. The historic reasons for why it's B are not so important right now, but we typically use a capital B for a indication of, or the variable corresponding to the magnetic field. And you'll notice that B is denoted as a vector because it, like the electric field, it has magnitude and direction. We define the direction of the magnetic field such that it is the direction which the compass needle will point. The north pole of that compass needle will point in the direction of the magnetic field, as we said earlier, and the south pole of the dipole will point opposite to the magnetic field. So what we saw here was how that direction of the field is defined. The strength of the field is proportional to the torque felt by the compass needle. So if we had a little torque meter that could tell us what the torque on that dipole is as a result of being immersed in the field, we could measure the strength or the magnitude of that magnetic field. Okay. Now, the magnetic field of a bar magnet actually looks very similar to that for an electric dipole. The picture here shows a sprinkling of little tiny magnetic filings made of iron that themselves, they're little long, small little pointed or little line segment pieces of iron filings. And you can see how if they're sprinkled on the table and then the magnet is placed on that table, how they will line themselves up along the field lines. And so you see the field lines look like they emerge, for example, from the North Pole right here. They look like they emerge from the North Pole and curve around to the South Pole. Or you could equally say they emerge from the South Pole and go around to the North Pole. The way the magnetic field is defined is it goes from the North to the South Pole, as we've drawn here. So all of these field lines represent the direction of the field as it's experienced by the iron filings in the vicinity of this bar magnet. Likewise, you see little compasses here. The one up here on the upper right is showing the field is vertical, upward, because of the orientation of that compass needle. The red end is the north pole of that little compass needle, and it points in the direction of the field. Likewise, here in the upper left compass, we see that the magnetic field is pointing down to the left. Upwards on the upper right compass, down to the left on the upper left compass. On the lower compass, we see that the magnet is pointing to the left, so that's the direction of the field in this particular location. Oops, sorry about that. I'm not very good at this. There. There's the direction of the field for the lower compass, and then for this compass right here, as you can see, the field is pointing away from the magnet. So if we were able to place a compass at lots and lots of different positions, we could trace out the shape of that field, much like we were able to do in tracing out the shape of an electric field using a test charge. Since these iron filings are not labeled, they themselves don't point in the direction of the field, and that's why we need the compass, the set of compasses to show us what that field looks like. So here would be an arrangement of compasses placed on the table and the orientations noted, which would allow us to trace the general shape of that magnetic field. The field lines are used as a device for us to understand magnetic fields, much as they are for the electric field. But it's basically true that in all of space surrounding a magnetic field or a magnetic dipole, it's filled with magnetic fields. It doesn't just exist at the locations of these individual compass needles, but in placing them in various locations like this, we can get the general gist of that field. If we want to represent the field at one particular point, we put the compass there and we find out which way it points and we draw the field. So you can see in this diagram how the field, the trend of the field is to move around in a circle from the North Pole to the South Pole. So you can see how the dipole field is evidenced by the response of these individual compass needles. So here's what the dipole field of a magnetic dipole looks like. This blue field here is drawn. It's very similar to that for the electric field. And here you see the iron filings surrounding a bar magnet and the adoption of the shape that they show as a result of the forces or the torques applied by the magnetic field from this dipole on those individual iron filings. We can also place a north pole of one magnet near a south pole of the other, which would be an attractive combination, and we can see what the field looks like there. You see how the north and south poles themselves form what looks like a dipole field right here. And in other regions, we see how the field acts as a result of these two poles being near one another. Notice between the two north and south poles, the field itself points from the North Pole to the South Pole, as we said earlier. Likewise, we can put two like poles together, like these two north poles, and that repulsive configuration ends up showing field lines which basically always point away from these two poles, as evidence of the repulsion between those two poles. The field lines don't start on one of these poles and end on the other, because field lines always start on the north and end on the south. So we would never see lines between these two poles joining the two, because they are like poles as opposed to opposite poles. Between two opposite poles, the field lines go from one pole to the other. There's another kind of magnet that many of us are familiar with, refrigerator magnets. We can form a strip of magnetism, a small plate of magnetism, inside of which the magnetism looks like short little U-shaped dipoles. And you'll notice that they're glued in place so that the north poles are near the north poles right here. These north poles are right near the north poles, and the south are near south. But in doing so, all of the magnetism exists, for the most part, in this upper region here, because that's where the tips of these bar magnets are. Down here, there is not nearly as much magnetism because the poles are both facing up. So the net result of this arrangement is that these U-shaped bar magnets go along the length of the magnet, so that we have a strip of north pole region, a strip of south, a strip of north, a strip of south. And as a result, when we place this surface up against a refrigerator, which has a lot of iron usually in the front plate of that, the front face of that refrigerator, this magnet will be attracted to that plate because the plate itself will adopt its own temporary magnetism to bring those two together and cause that force to make them stick. So the refrigerator magnet is really a bunch of magnets put together But you'll notice every one of these dipoles always has a north and a south pole. You can't divide them up. If we were to cut this little U-shaped magnet right along this place right here, we would end up producing two magnets. This one here on the left would have a south pole on the top and a north on the bottom, and the one over here would have a north pole on the top and a south pole on the bottom. All of that to say that no matter what we try and do, we can't separate out north and south poles. But this particular arrangement is very clever because it forms a large plane of alternating magnetism, north-south, north-south, which is then ready to stick to any iron substance like the face of a refrigerator, so that we can pin things to the refrigerator like family pictures and so forth, or advertisements. The magnetic field of the Earth is probably one of the greatest examples of magnetic fields we encounter on a daily basis. The Earth itself is a large dipole magnet. We believe that it's produced by circulating charged currents in the center region of the Earth, large iron currents that flow and produce this magnetic field. The actual production mechanism for this field is not entirely understood yet. But if you look at this top left picture, you see that the Earth, which is spherical, looks like a bar magnet. It looks like it has a bar magnet on the inside, but it's tilted with respect to the actual geographic pole, which is right here, the rotation pole. The Earth rotates on this axis right here, but the magnetic field, the magnetic dipole, is oriented along this line here. So there's about an 11-degree difference between those two, and that places the magnetic pole, what we associate with the pole in the north, actually located in northern Canada. It's located on land in some of the northernmost regions of the Canadian landmass. And it also turns out that the north pole of the Earth is actually a south magnetic pole, and the south pole of the Earth is actually a north magnetic pole. But that actually makes sense if we're going to define the field direction as that which would rotate a compass needle the way it does. The compass needle is oriented along this direction, which is from its south to its north pole. And the reason it points that way is because the north pole of the magnet lines up with the field lines. You'll notice the field lines here on the outside of the Earth point upward like this, but then they go through the Earth and back around. So inside the Earth, the actual direction of the magnetic field is downward, like that. Or the direction of the dipole is downward. The actual field lines emerge from the North Pole. Sorry about that for the confusion. The actual field lines emerge from the North Pole, go around to the south, and then they go back through the magnet and connect to themselves. As we're going to learn in a moment, magnetic field lines always exist as closed circles or closed curves. There is no beginning and ending to the magnetic field lines. They always are closed loops. We'll learn that in just a moment. So the Earth is like a large magnet. Its northern pole is actually a south magnetic pole, so that the north pole of the compass is attracted to it. So the very fact that we line up our pole, our compass needle, and we see that the north pole of the magnet is attracted to the northern region of the Earth is evidence of the fact that the actual magnetic pole at that location is a south magnetic pole. It's north geographic pole, it's south magnetic pole. Hope that's not too confusing, but it's an interesting piece of information that we don't often think about. There's also a dip angle. If you notice, if you look at us in Indiana, this is not the American continent that we see here, but the latitude of Indiana is right about here, and you see that the field lines enter the Earth at an angle. They don't point horizontally. Only at the equator down here do the actual field lines point in a direction that's parallel to the surface of the Earth. Likewise, at the pole, the field lines actually enter the Earth in a somewhat perpendicular fashion. So partway there, in Indiana, in the northern hemisphere, the field lines actually point north, but they also point down into the ground at a certain angle, and that angle is called the dip angle. So you might imagine a region fairly far north would have a steep dip angle, whereas a region of the Earth that's closer to the equator would have a shallower dip angle. And the dip angle is really an angle that's produced by the horizontal and vertical components of the magnetic field at that location. So in this particular location, the field line is coming into the Earth along this axis. Here's horizontal, and so the dip angle is what exists between the horizontal and the actual field direction. There are species of animals that we believe sense this dip angle and use it for navigation. We'll have something to say about that a little later. Okay, so in summary, the Earth itself is a large magnet. It has a dipole character, and it has allowed historically peoples to navigate over long distances by looking at the compass needle and the direction that it points. There are other ways in which people have navigated across large oceans, including looking at the stars, but magnetism has formed a mechanism by which we can find out directionality on the Earth and know which direction is north and which direction is south. Okay, there's a magnetotactic bacterium that contains a bunch of little iron pieces in it. Very basically, you can see a little string here of magnetic bits of iron in their bodies that allow them to sense the field. Basically, the magnetic filings or the magnetic pieces or bits in their body run along the length of the worm, and so when they're swimming in the water or moving around in the water, the line of their body can be lined up with the Earth's field because of those little iron filings inside them. Their bodies rotate to line up parallel to the Earth's field just like a compass, and because in the northern hemisphere, in the northern and southern hemisphere, there is a significant dip angle. In the northern hemisphere, if they follow the direction of the field, they would go down deeper into the water because the field line dips down into the Earth in the northern hemisphere. And so they can swim to deeper water by simply following the magnetic field lines, which is exactly what they do because they prefer the low oxygen region toward the bottom of the body of water. If the water is disturbed or they're displaced upwards, all they have to do is, again, follow that field line downward because they have that inbuilt compass which shows them the direction of the field.